Look around you. The spiral of a shell, the symmetry of a flower, the rhythm of seasons. These patterns existed long before humans invented mathematics. Early thinkers observed the stars, plants, shadows, and time. They noticed relationships. They searched for structure. Algebra was born as a language, a way to describe what nature was already showing us. Today, as our world faces complex challenges, reconnecting algebra with nature may be the key to redesigning a better future. Nature is the teacher. Mathematics is the translator. Before there were equations, there were questions. How tall is that tree? How much rain will fall? How long until winter returns? Early humans measure the world to survive. Over time, symbols like X, Y, H, and T emerged to represent what was unknown. Today, variables power science, engineering, coding, finance, and medicine. Sensors track temperature. Models track rainfall. Algorithms track behavior. But nature also reminds us of something important. Many variables, like climate and ecosystems, are deeply complex. Observing nature helps us to find the right unknowns before we try to solve them. Survival has always required solving problems. Early humans had to answer real questions. Where's water? How much food is enough? When should we move? Today, we solve unknowns in medicine, engineering, economics, and even space exploration. We calculate safe doses, stable structures, optimal costs, and spacecraft trajectories. Algebra helps transform questions into decisions. But now our unknowns are larger than ever. How much warming is too much? How much forest is enough? How much energy is sustainable? Algebra once helped us survive as individuals. Now it must help us survive as a species. Nature is not made of isolated parts. Everything is connected. More rain leads to more crops. Fewer trees lead to higher temperatures. More pollution leads to poorer health. Graphs and equations allow us to see these relationships clearly. They help us visualize cause and effect in science, economics, and society. When we understand relationships, we begin to see hidden system behavior, feedback loops, tipping points, and long-term consequences. And today, one truth is undeniable. Human actions are deeply connected to ecosystem and climate outcomes. Nature is not random. It is deeply patterned. Spirals and shells, symmetry in flowers, hexagons and honeycombs. These patterns inspired architecture, algorithms, financial models, and design systems. But what makes nature truly remarkable is efficiency. Strong structures with minimal material. Maximum function with minimal waste. Biomimicry is the idea that instead of forcing our own designs onto the world, we learn directly from nature's patterns. Nature optimizes. Algebra explains how. A forest is not just trees. It is a network. Food webs, river systems, ecosystems. These natural systems are resilient because everything is connected. Today, humans build systems too. The internet, databases, supply chains, smart cities. But there is a problem. Many human systems are disconnected from natural systems. When we design cities without water cycles in mind, we create floods. When we build industries without ecosystems in mind, we create pollution. Sustainable design requires ecosystem-level thinking. Nature already shows us how to build resilient systems. We must learn the structure. Real-world problems rarely depend on just one factor. Climate depends on oceans, forests, sunlight, industry, and atmosphere. Ecosystems depend on species, temperature, rainfall, and human behavior. Engineers solve many equations at once. Scientists model interacting systems. AI models use thousands of variables simultaneously. The biggest challenges of our time, climate change, sustainability, global health, cannot be solved with simple thinking. They require systems-level modeling. The future belongs to those who can understand complexity. Nature does not guarantee outcomes. Weather is uncertain. Survival is uncertain. Evolution itself is uncertain. That's why seeds spread widely, because survival is never guaranteed. Probability gives us the tools to reason in uncertainty. We use it to manage risk in finance. to evaluate outcomes in medicine, to design safety in engineering. And when scientists predict climate futures, they use probabilistic models, not certainty, but likelihood. Nature survives because it plans for uncertainty. So must we. Nothing in nature is static. Rivers flow, populations change, ecosystems shift, rates of change appear everywhere. In motion, in economics, in disease spread, in technology growth. Calculus gives us tools to understand how fast change is happening, where growth accelerates, where systems begin to collapse. Today, understanding change is no longer academic. We must understand the rate of climate change, the speed of biodiversity loss, the acceleration of urban expansion. Because if we cannot understand change, we cannot guide the future. Humans learned algebra by observing nature. We use this knowledge to build civilization, technology, and infrastructure. But somewhere along the way, we disconnected our systems from the wisdom of nature. That disconnection has led to imbalance, environmental, social, and systemic. Now the future demands a new way forward. We must return to nature, not just for inspiration, but for understanding. Learn algebra from nature again. Model systems like ecosystems. Design like forests. Optimize like evolution. Because the next generation of innovation must not fight nature. It must learn from it, align with it. And through that, we can redesign the world sustainably.